you notice that we discussed about the DC biasing or placing the transistor on the load line. And as I mentioned a few times until now, we can place the transistor on the load line and we may have, three different regions. On the left side is the saturation. The middle side or the active region means that the transistor is placed on the active or linear region. And on the lower side, or any values below the x-axis, that's the cutoff. Now, going into the linear region means that we are trying, to place the transistor as close as possible to the midpoint between the extreme values, the mean and the max in terms of the voltage or in terms of the current. Means that the largest current, or it's, the saturation current, that's the maximum current, which is given by the supplied voltage, the RC, eventually, the RE, as in this circuit. And the other extreme point is actually the supplied voltage, which is the VC max. The VC max, it's equal with, the VCC, or the supplied voltage on the collector. Now, once, the transistor is placed on the, closer or in the mid-range of the load line, we can apply an AC input voltage. You notice that the Vin is a small signal in terms of the voltage, or can be expressed, in terms of the current. As the voltage is changed, the current, the IB current is changed, means that we have, a swing in the IB value. In this example shows, the saturation, the Q point, the IB is 50 microamps, and you notice that the IC is 5 milliamps. Means that the input voltage or the input current may swing, between, in this example, between 40 microamps and 60 microamps. Now, what's the effect of having, a change in the input voltage or the input current? The output voltage or the output current, it's a replica of the input voltage. But you notice that, the amplitude is much greater than the input, and in top of that, you notice that I'm having the phase shift between the input and the output with 180 degrees. Means that if the input is positive, you notice that the output is negative, and vice versa. If the input is negative, the output is positive. Means that the same signal or the same voltage or the same current applied on the base is amplified, or it has a gain in voltage or a gain in current or a gain in power as is collected on the output of the amplifier. You notice that that's the circuit that I already used in the first, the second lab, which has, the three capacitors. And now we have to talk about, those three capacitors. And what's the purpose of those capacitors we'll discuss today. You notice that once, we are applying a change in the input signal or a change in the input or the base current, it will reflect this current on the output as a change in the IC. You notice that the current is in phase with the collector current is in phase with the base current, but in terms of the voltage, and this is what we are connecting. We are connecting a load into the collector of the transistor. In terms of the voltage is exactly the opposite, means that the phase shift on the output voltage is 180 degrees out of phase with the input voltage or the input signal. Now that's a very or a clean diagram that represents the same thing. I'm applying a swing in the or a change in the IB or a small signal on the base of the transistor. In the same fashion, in the same way, the IC will change with a different value. It means that I'm getting a gain or an amplification in the collector. And in terms of the voltage, again, we'll have the same swing or the same replica of the input voltage or the input current, except that the collector voltage is 180 degrees out of phase with the input voltage. Now, if we are looking to find what is the AC behavior, up to this point we discussed about the DC behavior, or how to bias or properly bias, or how to determine the bias of the transistor. But in top of that, now we are applying an AC voltage or an AC signal on top of the DC component that is due to the Q point. If you remember in ELE350, I introduced the superimposing an AC voltage on a DC voltage. If that's the DC voltage, I'm making the assumption that's the DC voltage that is created by the biasing of a transistor. Now we are applying an AC signal which superimposed on a DC voltage. You notice that the DC voltage is above the x-axis, and if we are not placing the transistor in with the proper bias, some of these waveforms may be clipped. Means that I have a limitation on the upper side. Means that the top side may be clipped, or the signal or the output signal, it will be distorted. Or if we are placing the DC voltage a bit lower, let's say on this side of the or this value of the DC voltage, the lower side of the signal, it may be clipped. Means that that's the precaution that we have to make sure that the signal is not clipped, or is the signal is not distorted as is amplified by a transistor or by an amplifier. Now, for this type of amplifier, which is the simplest amplifier, in order to determine what is the input resistance, or as the input impedance of the circuit. Now you notice that we have different equation or different formula to determine what is the total resistance or the total impedance of the circuit as an AC signal is applied. And you notice that I choose to use a different beta, which is the beta AC. Means that that's the beta that may be used in AC analysis. And these values may be different than the DC beta. You notice that in DC beta in this circuit is 150, but in AC the beta may be changed to 160, or can be higher. Again, we'll see a bit later, and we'll discuss about the purpose of having the C2 in the circuit. Now, in order to determine the total resistance of the circuit, in the equations, that's the RE1, means that that's the resistance in the emitter in DC, but in top of that I have the RE, which is the emitter resistance. Now the question is how we can determine this value. This value depends on the emitter current and millivolts over the emitter curve. That's one way or an easy way to determine the RE or the base emitter resistance based on the emitter curve. Now I have to make the RE model, or how we can have the model of the transistor for the AC analysis. Okay, now if you remember, we talk about the current sources in ELE350. Now I can analyze, or I can replace the transistor to be analyzed in AC, which is more complicated than DC. In DC is the biasing, is just a few equations or a few rules that may be applied for DC analysis or DC biasing. For an AC model of a transistor, which is called the RE model, or the dynamic resistance of the transistor. Now, from the left side to the right side, that's the base of the transistor. That's the emitter, and the other one is the collector of the transistor. Means that in AC analysis, we have to replace the transistor with the RE model, which has an input impedance, has a current a current source, which is actually controlled by the base curve. Remember that by definition, a transistor is a three-terminal device that is controlled by a current, or is a current control device. Remember that, because on Friday, when I will talk about the FETs, we'll see the difference between BJT and FET. Remember that a BJT is a current control device. Means that controlling the IB, or changing the IB through the beta, or the gain of the transistor, where we are changing the collector current. Now we have the output. Again, if I'm looking from the load point of view into the circuit, into the transistor, I have the Z out, or the output impedance, in parallel with the current source. On the input, just having a pure resistance. Suppose that I don't have any other components connected to the circuit. You notice that the Zin, or Zin value, or can be defined as the beta RE. Again, is the RE model, or the RE equivalent model for a transistor that can be used in AC analysis. On the output, I have the collector and the emitter, and the output impedance of the transistor between the collector and the emitter, or we can approximate that as an infinite ohmic value, or an infinite resistance. Now, a multi-stage amplifiers, in some applications or some cases, we may have to apply 2 or 3 or 4 or 5 stages to amplify a signal. In this example, it's using a very small input voltage. Suppose that that's 100 microamps, and we want to get an output in 1.35 volts. Most of the time, you are not seeing the circuits that has 500 or 800 gain. Usually, what you are seeing multiple stages, and each stage has a certain gain. As a rule, or as a recommendation, I'm not saying always is a rule. That's why I will take it as a recommendation. The first stage, it's used in few tens, like 50, 20, up to 100. And on the second stage, I will choose here a gain much higher than the first stage. Usually we have, multiple stages that are connected or are linked through a capacitor. And you notice that I'm having the capacitor C1, capacitor C3, capacitor C5 that may be connected to another stage or another amplifier, or may be connected to a load. Means that if that's the output, I will connect, the load resistance to the ground, and uh, the the purpose of those capacitors is to let just the AC component to pass through the capacitor. And in the same way, the C3 makes the connection or the uh, filtering the AC component and the DC component. Means that the C1, C3, and C5 in this diagram, it will have the ability of letting just the AC component to pass through. If, and I'll make this example, suppose that I'm not having this capacitor connected between the two stages. You notice that the Q point on the first stage is affected by connecting, the other resistance or resistances or the other circuit on the collector of the first stage. And that's why, we are not using, a direct connection between, for example, the collector and the load. Again, I make, the same assumption that, the C5 is not present in the circuit. The R5, it's, or the current that flows to the R5, that's, the current that flows to the R5. It's split it in two currents. One current goes through the RL or the load resistance, and the other current goes, between the collector and the emitter. Means that the load resistance affects the Q point, may change the Q point, and this is what we try to avoid to maintain the transistor on the load line without changing the Q point or the steady value of the collector current. That's why the purpose of those capacitors is a coupling capacitor between the input voltage and the first stage, a coupling capacitor between two stages, or a coupling capacitor between an amplifier or a circuit and a load. Means that those capacitors, it will allow to pass just the AC voltage through them, not the DC component. To remind you about a capacitor, what a capacitor does in DC circuits, it will block the DC circuits or the DC voltage, and it will act as like a short circuit, which will allow to pass just the AC component from one stage to another stage, or from the input voltage source into the first stage, the output voltage source, the AC component of the output voltage into the resistance value or the load of the circuit. Now, the approach that we discussed, I already introduced, the purpose of the C1 and C3, but you notice that in the same time I'm having, a capacitor across the RE resistors. I introduce and I use, a circuit similarly that, just to become familiar with the basic arrangement of the external components around a transistor. And now we can discuss, the applications for a BJT. But in the same time, aside, we have a diagram using a JFET. You notice that is an FET. That's a field effect transistor. And on Friday, I mentioned that we'll discuss about the last topic of this unit, the FETs. and we'll talk about the JFETs and E and CMOS technology. But at this point, remember that the C2, it's used, to in parallel with the RE. To remind you about, the reactance of a capacitor. And that's actually an improvement on the response of the transistor. And the next lab, in the computer lab, will see the effect of the C2 when it's removed from a circuit, and what is the purpose of having the capacitor around or across the RE or the emitter resistors. I mentioned that without disturbing the Q point, and this is our main goal, without disturbing the Q point. Suppose that we are not using the C1 or C3, and I mentioned that if we are not using the C1 or C3, the resistance RL, it will disturb, it will move, it will change the Q point of the transistor. And in the same way, if I'm not using, or if we are not using the C1, it will disturb the Q point, because remember that we have a resistor which is actually the internal resistance of the V in. And in AC analysis, I will give just an idea about the AC analysis. The capacitors are short-circuited and the voltage sources are replaced with a short circuit. Now, I mentioned that, the first two are pretty large values resistance, and those are coupling capacitor. C1, C3 are large capacitors, and those are called, coupling or connecting, the two stages, or to make, to let just the AC voltage and blocking the DC component of the circuit to the load, or blocking the DC component from the input voltage into the circuit. The C2 is a bypass capacitor. Usually it's to lower the RE value due to an increase in frequency. Now let's go back to this diagram. Now I'm trying to recall the value of the AC. Now let's see if I can get that's the XC, and the XC, remember, that is 1 over 2 pi FC. Means that at very high or very low frequencies, the reactance is very large, and as we are increasing the frequency, the reactance of the capacitor becomes very small. Means that it will enhance, or it will increase actually the gain as the frequency of the input voltage is increased. You notice that at low frequencies has almost no effect on the gain as the frequency is increased. And that's the last part of the lecture. There is a limitation and there is a drop in the gain as the frequency is increased. The capacitor, it will improve, or it will make a better response or a better characteristic as the frequency of the input signal is increased. And you notice that as we are increasing the frequency, it will decrease the XC, but the capacitor is connected in parallel with the RE. Means that we easily can calculate the gain of the circuit as the RC over RE. But RE has the capacitor connected across, means that the RE value or the impedance of the RE and the C2 becomes lower as the frequency is increased, which will compensate the drop in the gain or the drop in the output voltage for or above a certain frequency, which is called the critical frequency. Now, I include, the DC analysis and the AC analysis, and I made, the DC equivalent of a BJT. Remember that what a capacitor does in DC, it will charge and to remain charged, means that in DC analysis, due to the capacitor C1 and the C3, and the capacitor or the capacitor, it will isolate the input voltage V in. The load resistance means that there is no current or no voltage applied to the RL. And if you remember, I made you measure the voltage across RL in DC, and you notice that the voltage VRL in DC, it was 0 due to the capacitor that is connected between the collector and the load resistance. For an AC analysis, we have to make a different approach. Again, I'm just showing, I'm not going into details because it's more complicated than DC. For an AC equivalent circuit, you notice that I'm replacing, and that's the rule for AC analysis. The capacitor are replaced with a short circuit, and the voltage sources are replaced with a short circuit. You notice that instead of having the DC voltage source, that's the DC voltage source, I replace the DC voltage source with a short circuit. Now, if I'm looking into the transistor or into the circuit from the voltage, from the input voltage, I'm seeing 3 or 4 transistors connected to the ground. Means that the analysis of this circuit, you notice that I'm having the R1 connected to the ground, I'm having the R2 connected to the ground, and on the load side or on the collector, I have the RC connected to the ground and the RE connected to the ground. In top of that, I have to replace probably the transistor with the RE model, and now we are starting into the AC analysis. Again, we are not going into the AC analysis. I'm just showing, what are the changes and what are the rules for the AC analysis. And I mentioned that the capacitor effect, or what a capacitor does. If you remember when I showed to you the specs of a transistor, I emphasize that there is always a capacitance between the base and the collector, and the base and the emitter. I know it's very small. I'm talking about, few picofarads, like 4, 6, 8, 10 picofarads. Means that is very small, which will affect actually the response time for a high frequency. In the same way, we can look for the FET that I will introduce on Friday as a capacitance between the drain and the gate, and the source and the gate. You notice that I'm using a different terminology or different name for those 3 terminals or those 3 leads of an FET. But again, I will explain in the Friday's lecture. Most of the time you will see the frequency response, or how the circuit it will behave as the frequencies increase or decrease. Most of the time you will see the frequency response in dBs or decibels. Now we have to make the definition, or how we can calculate the AP. That's the notation that it's used for a gain in power or a gain in voltage. Remember that A, and that's the easiest way. It's a gain. If is a P, that's a gain in power. If is a V, it's a gain in voltage. Now we'll use, a bit later in the operational amplifier as A as the gain. You notice that the amplification or the attenuation. If the ratio of the output voltage over the input voltage is greater than 1, means that I'm having, a gain. I'm having, an amplification on the input voltage. The the uh, the gain actually it's an amplification. I mentioned that if A is greater than 1, let's say it's, the ratio of the V out over the V in. That's, the V in. If this ratio is greater than 1, A is an amplification, means that the output voltage is amplified with respect to the input voltage. But in the same time, we may have, the output voltage less than the input voltage. That's an attenuation, means that I can make, the gain or the amplification less than 1, which makes an attenuation. This is what we are doing when we are adjusting, the scale on the oscilloscope. We may use the input um, stage of the oscilloscope to amplify or to attenuate actually the input signal. Now we have, the two relationship or the two ways of um, um, evaluating, the gain in terms of the power or in terms of the voltage. Sometimes you will see, the AP or the gain in power, and we can calculate the gain in power as 10 log of AP. AP again, in the same way, if I'm replacing the voltage with the power, I have the P out over the P in. Means that that's, the gain in power. If we have, the voltage or the output voltage and the output current, it's 20 log of AV or the gain in voltage. All these, scales, it's a logarithm. It's the use of, logarithmic scale. Now the question is why it's used a logarithmic scale. Remember that we are dealing with a very large range of frequency from few hertz. Let's say, I'm starting with 1 to 10 hertz up to giga, mega, kilohertz. Means that the range in frequency, it's a very large response of the frequency that may be applied to an amplifier, to a circuit. That's why in order to make, a bit smaller diagram in terms of the range of frequency, they are using a logarithmic scale. What a log function or a logarithmic measurement does, it will compress or it will minimize actually the scale or the base that it's used to evaluate the response time for a circuit. In terms of the drop in value, in terms of the voltage or in terms of the power, 3 dBs, which is about 70.7% drop in the value. For power, you may see another notation or another unit, which is the dBm. When it's used the 1 milliwatt power as the reference, or the 0 dBm, you notice that it's in terms of the power, or it's in terms of the 1 milliwatt power. 0 dBm is equal with 1 milliwatt. Now the question is, again, the frequency response. Suppose that we are going, a frequency lower than a critical frequency when the amplification or the gain is dropping by 3 dBs. In this example shows, a drop in gain or a drop in amplification as the frequency of the input signal it's less than a critical frequency. You notice that I'm having, the FC. Now I can have, the decade means that I'm going, from FC to zero point 0.1 FC, which is a decade. A decade of 0.1 is 0.01 FC, and so on. Means that the frequency response or how the circuit it will behave as the frequency is increased or the frequency is decreased. You notice that in this example, the frequency is decreasing, means that we are looking to analyze what is the response of the circuit of the amplifier as the frequency is increased or decreased. Now we may see instead of an decade, we may see an octave, which is the frequency that doubles or having the half of the frequency. We are not using too much, but just in case you may see as the frequency it's double, and that's the Bode plot or the response or the analysis of AC behavior of a circuit from a low frequency to a high frequency. These plots are mostly referred as Bode plot or the Bode analysis from a low frequency to a high frequency. And you notice that most of the time the drop in gain is about 20 dBs or decibels per decade. On a high frequency, again, suppose that I have a steady gain or the steady frequency or the steady gain for a circuit up to a certain frequency. Above that frequency, remember that all the capacitors that we have in the circuit, it will affect or it will change the response of the circuit in terms of the gain. You notice that above a certain frequency, there is a drop in voltage by 20 degrees per decade, and actually, or above a certain other frequencies, the drop in gain may be a bit higher. Now, if we are trying, to put together to define the bandwidth for an amplifier, a bandwidth for a receiver, in the same way, we have to define what is the minimum or the lower critical frequency and what is the critical frequency, but the upper frequency. You notice that in the bandwidth is defined when the gain of a circuit, of a receiver, of an amplifier is almost constant, or this is what we are looking for. Means that for any signals with a frequency between the two limits, the FCL, that's the cut off on the lower frequency, that's the cut off on the upper frequency. Any signals that is applied between the two limits, which is called the bandwidth of an amplifier, the bandwidth of a stage, the bandwidth of a receiver, it will have a constant gain. Anything above or below those two frequencies, it will be a cutoff. Usually it's a 20 dBs per decade on the upper or on the lower frequency. An application for that. When you are looking to buy, for example, a receiver or an amplifier, an audio receiver or an audio amplifier, we are looking for a low frequency. That's the cutoff frequency, means that the vendor, it will guarantee that any frequencies from, let's say, 20 hertz up to 20 or 30 kilohertz will not be distorted, or the distortion or the waveform on the output has, a very small percentage, as 0.1, 0.01, 0.03, and so on. Means that almost, the same input signal, it's amplified without altering, without changing actually the shape or the waveform on the input voltage. And these frequencies, again, we have to make sure that we are using, any signals in this bandwidth. Usually this bandwidth, um, we are designing, we are making, sure that, the bandwidth of the of a stage, of a transistor, of an amplifier, it's a bit larger than is required in the theoretical values, just to make sure that we are having, a good, stable, or constant gain as the frequency is increased or decreased between the two limits, the lower critical value and the upper critical value. And I will use again those two new limits, the FCL and the FCU, critical lower or the frequency, the critical frequency on the lower frequency, and the critical frequency on the upper frequency for the op amps. Any questions, comments, concerns, please? Again, if your test is tomorrow, again, don't worry, I'm not doing, anything new. I will go over, the same lecture with probably the second half of this class, which probably they have, the tests right now. Just in case, do you have, another midterm exam or midterm test like this one in the next probably 4 or 5 weeks? Just give me, some heads up if you have, any other tests like, this one, to see what we can do, what we can accommodate that. Are you aware of, any other exams or tests in the next 4 weeks, 5 weeks from now on? No, not yet.